Okay, so today we're going to talk about the inverses of quadratic functions. So for this first task, it says when people first learn to drive, they're often told that the faster they are driving, the longer it will take to stop. So when you're driving on the freeway, you should leave more space between your car and the car that is in front of you than when you're driving slowly through a neighborhood. Have you ever wondered about the relationship between how fast you're driving and how far you'll travel before you stop after hitting the brakes? Think about it for a minute. What factors do you think might make a difference in how far a car travels after hitting the brakes? So take a second to pause the video and write down some things. Okay, so just your answers, of course, are going to vary here, but for example, you could say speed, friction, the incline if you're going up a hill or if you're going down a hill, road conditions such as the weather, the surface, the type and tread of tires, the weight of the car. There's many other possible answers you could put here. So I'm just going to write answers will vary. There's actually been quite a bit of experimental work done, mostly by police departments and insurance companies, to be able to mathematically model the relationship between the speed of the car and the braking distance, which is how far the car goes until it stops after the driver hits the brakes. So imagine your dream car. Maybe it's a Ferrari 500, Maranello, a super fast Italian car. Experiments have shown that on smooth dry roads, the relationship between the braking distance d and the speed s is given by this equation right here. Notice that this has a square in the equation, so this is a quadratic equation. Speed is given in miles per hour and the distance is in feet. So for A, it says how many feet should you leave between your car um, in the car in front of you if you are driving the Ferrari at 55 miles per hour. So you guys should pause the video and answer these next questions on your own. And then when you're done, you can unpause the video to check your work. So for this one, we know that d of s equals 0.03 s squared. So that means that if you are driving 55 miles per hour, that is your S. So we're plugging that in for S into our equation. So D of 55 is equal to 0.03 times 55 squared. So if you're doing this in your calculator, make sure you put that 55 in parentheses because remember you want to do the order of operations, PEMDAS. So we would do the 55 squared times 0.03. And when we do that in our calculator, you can see that we get 90.75. So we can go ahead and put that here. And of course, we're talking about feet. So when you're driving that fast, that's how many feet you should leave between the car and the car in front of you. So then it says, what distance should you keep between you and the car in front of you if you're driving 100 miles per hour? So now we're saying d of 100 is equal to 0.03 times 100 squared. So if you plug that into your calculator, you get 300 feet. You could also do that in your head. So for C, it says if an average car is about 16 feet long, about how many car lengths should you have between you and the car in front of you if you're driving 100 miles per hour? So for this one, you can go ahead and use your previous answers to kind of help you figure out what you need to do here. So we said if you're driving 100 miles per hour, recall that that was a distance of 300 feet. So we already found 100 miles per hour is 300 feet. And if your average car is 16 feet long, you are just going to be dividing that. So 300 feet divided by 16 feet is equal to, if you divide that using your calculator, you get 18.75 or 19 car lengths. Since we don't have part of a car. And for D, it says it makes sense to a lot of people that if the car is moving at some speed and then goes twice as fast, the braking distance will be twice as far. Is that true? Explain why or why not. Again, answer this on your own, and then when you're done, you can unpause. So the answer is no. The braking distance is a function of the square of the speed. So it's not going to be twice long, and you can do some examples to kind of show that. So if we were to do d of 50, we would get 0.03 times 50 squared, and that gives us 75. And so double that is 100, so d of 100, we'd said up above that that was equal to 300 feet. And so you notice that 75, if we were to multiply that by 2, we do not get 300. So 75 times 2 is 150. So that is why this is not double the speed, because again, you're doing the square of the speed. So for question 3, it says graph the relationship between the braking distance d of s and the speed of s below, then describe all the mathematical features of the relationship modeled by the function. So make sure you are labeling, so this is the speed in miles per hour, and then the braking distance is the y-axis. And that's of course in feet. So we can just make our table s and d of s. So 0 would be 0. If we did 25, we would get 18.75 because we did that on the other page. 50, when we plugged that in, we had said it was 75. We did 100 on the other page, and that was 300. And if I do 200 and plug it into my equation, I get 1,200 or 1,200. So for this, we have 0, 0 and 2518.75. So these are going by 100 on the y-axis, so 2518.75 would be somewhere here. It looks like the x-axis is going by tens. 50 and 75. And then we have 100 and 300. And 200 and 1,200. And so this is what our graph looks like. So you can see that, again, just by looking at the equation and the graph, this is a quadratic function. So remember that the shape of the graph is called a parabola. And notice that we only have the first quadrant. So we're in quadrant 1 because we can't have negative speed or distance. So the domain of this is from 0 to infinity, and the range would be also 0 to infinity. So then question 4 says, what if the driver of the Ferrari 550 was cruising along and suddenly hits the brake to stop because she saw a cat in the road? She skidded to a stop and missed the cat. She measured the skid marks left by the car so that she knew her braking distance was 31 feet. How fast was she going? So now we are going to be plugging that 31 into our equation for d of s. We remember we have d of s equals 0.03 s squared. So now we're plugging 31 in for d of s equals 0.03 s squared. We're trying to solve for s. So remember when you're solving the equation, you do PEMDAS backwards. So we're trying to solve for the variable s, so you get rid of things added or subtracted to the variable, which we do not have. Then you get rid of things multiplied or divided. Then you do the exponent and parentheses. So first we want to get rid of that 0.03 by dividing it. And I can go ahead and leave it like this for right now before simplifying, because I can do that in my calculator. So 31 divided by 0.03 is equal to s squared. Now I can do the exponent. So how do I get rid of a power of 2? Remember, when you do that, you take the square root. And every time you get rid of even power, you need plus or minus the square root. But of course, we know we're not going to be using the negative because we don't have negative distances. So in our calculator, we can go ahead and plug this in. So I'm going to do this square root and first, and then use parentheses, and we have 31 divided by 0.03, and enter, and I get 32.1, and if we round this right here, we get 1.5. So 32.15, and remember this is miles per hour because we were finding the speed. If she didn't see the cat until she was 15 feet away, what is the fastest speed she could be traveling before braking and still missing the cat? So we're going to do the same thing. So 15 equals 0.03 s squared, the speed squared. So divide by 0.03. And then, of course, we want to then after that take the square root of both sides. So I'm going to wait just a minute so it doesn't get confusing. So we would get s is equal to the square root of 15 divided by 0.03. When you plug that into your calculator, you should get 22.36 miles per hour. So for the next one, it says, part of the job of a police officer is to investigate traffic accidents and determine what caused the accident and which driver was at fault. They measure the braking distance using skid marks and calculate the speeds using mathematical relationships as we have here. Create a table that shows the speed the car was traveling based upon the braking distance. So the distance would be your x, or in this case, we're using d for distance. And this is going to be the y, the speed. So we're now doing s of d. So if the distance is 0, then the speed would be 0, of course. And we can actually use the table that we did right up here, because remember that we really are undoing what we did. When you undo what you've done before to solve, that means you're doing the inverse. So I know that these values for d of s, I can just switch them in my table down here. So 18.75 is 25, 75 is 50, 300 and 100, and 1,200 and 200. Then it says write an equation for the function s of d that gives the speed of the car for given braking distance. So we have the distance equals 0.03 s squared. So now we want to solve for s to write our new equation. So what do we do first? We do the order of operations backwards. So divide both sides by 0.03. So now we have d over 0.03 equals s squared. How do we get rid of that squared? We take the square root of both sides, and of course, remember, we usually do plus or minus, but since we're talking about distances and speeds, we don't use a plus or minus. And so in this case, we get s is equal to the square root of d divided by 0.03. And if we use our notation, that means this is just s of d equals the square root of d divided by 0.03. And so that would be the equation we were using. So for 7, it says to graph the function s of d below, then describe all its mathematical features. So I want you guys to pause the video, and then when you're done, you can unpause it and we'll check our work. So we have our equation, and I just plugged in values for d and then did s of d and graphed my equation. And so this is the inverse of the quadratic, which is a square root function. So this is a square root function, which we can tell because there's a square root in the actual equation. And the domain of this we can see is from 0 to infinity, and the range is also 0 to infinity. And if we were to use our graphing calculator to take a look at this, I plugged it into y1 and y2. So in y1, if I go ahead and graph, notice that if I graph this, it gives me the full parabola shape. But remember, we can't have negative distances and speed. So this part on the left is not actually there. So I'm going to fix my graphing calculator. And so if I fix this equation, I can actually restrict the domain values to x values that are just greater than 0. So if I hit graph now, you'll see it's only going to graph this side of the parabola. And we can even make our window a little bit larger just to kind of get an idea what the graph looks like. And then if we go back to our y equals and graph our inverse equation, which is the square root of x divided by 0.03. So I'm going to put that on, and I'm going to make this a little bit thicker of a line so you can see the difference. That would be my inverse graph, which is square roots, which goes this way. And remember, we said the other day that these equations are reflections across the line y equals x. So in my calculator, if I put just x, I can see that if I were to fold my graph in half on the line y equals x, this graph would match up with this graph here. So from question 8, it says, what do you know about the graph of s of d compared to the graph of d of s? What's their relationship? And of course, we've already said this before. They are inverses because we switch the domain and the range, or the inputs and the outputs. Now it says consider the function d of s equals this function over the domain of all real numbers, not just the domain of the context. How does the graph change in number 3? So the graph that we did number 3, remember, was only part of the parabola, and we just showed on the graphing calculator that the way that the graph would change if we use the domain of all real numbers instead, it would look like this right here. So this would be the domain of all real numbers. Instead of just 0 to infinity, the range is still 0 to infinity. So the graph would show the entire parabola instead of just half. Then question 10 says, how does changing the domain of d of s change the graph of the inverse in d of s? So the graph would become the parabola opening to the right. So if we were to think about reflecting this across the line y equals x, our graph, remember, went this way for the square root function. And so that was this portion. So this portion, if we reflected over y equals x, would be down here. So it would look like this. So the graph would become a parabola opening to the right. So recall the inverse is a reflection across the line y equals x. And so the domain of this graph is still bracket 0 to infinity, and the range then is all real numbers. And so that makes sense because remember, you switch your domain and your range of your inverse function. So if we use the domain as all real numbers, then the inverse range would be all real numbers, and the range was 0 to infinity here, so the domain is 0 to infinity, because remember, you switch the two. So question 11 says, is the inverse of d of s a function? Justify your answer. So for d of s, remember that was the question number 9. So just to graph it again, remember that when we want to find out the inverse of the function, we use the horizontal line test. So if I were to take a horizontal line and move it up and down on this graph, notice that it hits in more than just one spot. Therefore, it does not pass the horizontal line test. So d of s doesn't pass the horizontal line test. Thus, the inverse is not a function. And we could also have seen that from looking at question number 10. If I actually look at the graph, I could use the vertical line test on the actual inverse graph. And if I use the vertical line test on the actual graph, I can see that it doesn't pass the vertical line test, and therefore it's not a function. But it was asking us to look at d of s instead of this graph here. So then for the next one, it says, what types of functions have inverses that are also functions? All right, so it says what types of functions have inverses that are also functions. So recall, functions that have only one output for each input have an inverse that is also a function. Remember, we talked about one-to-one function the other day. So recall that means that if the graph is one-to-one, which means it passes the horizontal line test, then its inverse is a function. And for question 13, it says, a function whose inverse is also a function is called invertible. What are the characteristics of invertible functions? So remember that invertible just means that it's one-to-one. And the function must pass the horizontal line test for it to be invertible. Each input has one and only one output, and each output has one and only one input. All right, so this is what we just said. So again, the function must pass the horizontal line test to be invertible. So remember, for something to be a function, it has to pass the vertical line test. Each input has to have one and only one output. And for the inverse to be a function, each output has to have one and only one input. And so that's just our definitions that we used the other day. And remember, that means that our function, if it is one-to-one, then the inverse is a function. So that is the terminology that we use.